Thank you very much, Barbara. And first of all, let me start by thanking the organizers, Anastasia and Stefano, for the kind invitation. I think it's my third time here giving a talk, and I'm always happy to come back. And also thank you all for being here after lunch, rushing for the, for the afternoon session. So the topic I'm going to present to you is a topic in, I would say, more in the variational than the geometrical theme of the conference, and it's about defects in crystalline solids. I'm confident that many of you have heard about dislocations, at least in the half of the audience who is familiar with this type of problems in continuum mechanics. Disclinations are a little bit more obscure than dislocations, and I'll try to give a general overview to everybody so that you can follow. Also, let me, before starting, acknowledge my two collaborators on this work, that are Pierluigi Cesana from Kyushu University and Lucia De Luca from the CNR in Rome. So the menu for today's talk is the following one. So we're going to see what dislocations and disclinations are. And the idea that we got to try and frame disclinations in a variational framework is to find an appropriate energy functional written in the Airy variable, which is kind of a trick very popular in the engineering community when you've got a two-dimensional problem and you want the equilibrium equation, so the divergence of the stress equal to 0, to be automatically satisfied. And if you've got a material without any defects, the elasticity is called compatible, and dislocations and disclinations arise when there is some kinematic incompatibility. So I'm going to go through a little bit of a review of compatibility and incompatibility to see where the measure of these defects arise and how they can be treated. And then we can move on to systems, finite systems of isolated disclinations, and we see the energetics of them. And then we would like to study what happens when you've got two disclinations that are very close to one another. So as we will see, they interact in a fashion that's like electric charges. So to each of these defects, we can associate a plus or a minus sign in a way. And so you expect that they behave like electric charges. Opposite signs attract, equal signs repel. And there's a construction by Eshelby, dating back to 1966, according to which one dipole of disclinations is equivalent to one edge dislocation. And we managed to give it a formal statement and an accurate limit in terms of finding the energy scaling, which is the correct one to see things properly. And with this, we take a dipole of disclinations, we obtain, in a way, one edge dislocation, and we can, in this section here, when I say limits to dislocation, we can recover results that are known since about almost 20 years now about edge dislocations. So let me mention that dislocations and disclinations popped in Vito Volterra's mind at the beginning of 1900 when he did some thought experiments, and he considered a hollow cylinder. He cut a slice, he cut like a section in one of these parallel to the axis, and decided to see how the fields arrange if you use the general 3 modes of fracture. So mode 1 is opening, mode 2 is sliding, mode 3 is like the antiplane shear deformation. And he devised that there should be some incompatibility arising, and that's what he called dislocations, and they are defects that arise in the translational part of the deformation gradient, whereas disclinations happen when you've got a wedge of your material and then you do overlapping of some sort. So either you open radially, or in the angular variable, or you do overlapping, and these are the disclinations. So dislocations are modeled through are characterized by their Burger's vector, which in the case of edge dislocations is perpendicular to the dislocation line. So a dislocation line is a line of these defects appearing in a material which is defective. And it's in a way the way that the lattice mismatch happens across this line is that it goes perpendicularly to the line of the dislocations, whereas for the other type of dislocations that are the screw dislocations, those are easily thought of when you're tearing apart a piece of paper. So if you imagine that you've got a cross-section of your material, which is a piece of paper, you tear it apart, and then the deformation that you make is like if you go up one staircase in these spiraling staircases. And in that case, the Berger's vector that measures the discrepancy of your lattice matching is perpendicular to the dislocation line. But for us, edge dislocations are important, so the other ones. And disclinations, on the other hand, are, as I said, failure of the closure for a closed circuit when you do a rotational movement. And they're called wedge disclinations, and they can be measured as positive or negative defects according to a preference that you might have, and in the engineering community usually are in this fashion here. So think of taking your favorite Zuckertorte, you cut out a wedge of Zuckertorte, and then you glue it up together. You obtain a five-fold, which is this one, which is conventionally called as a positive disclination. Whereas if you cut open a slice of your Zuckertorte, then you insert the wedge that you took out of the first one, and then there's not enough room, so that the material needs to deform in this way, and you have a seven-fold defect in this way. So you would have five wedges in place of six. So if you think of an hexagonal lattice, or you have 7 wedges in place of 6, that would be the equilibrium. And things would be very nice if your sheet of material could go out of plane. So if you allow for out of plane deformation, then you form something which is cone-like, and it stores very little elastic energy. But if you confine your material to stay in plane, which is what happens in many materials or in many models, for instance with graphene, then you really do have deformations, and then there's elastic energy stored in it. The title carried the name semi-discrete modeling, and the semi-ness comes in the fact that we count the defects individually. So there's capital N of them, say capital K or whatever the letter will be later on. But then the substrate, the material, is modeled through continuum mechanics. So you would see this sort of interplay between scales where when it comes to defects, you really count kind of the bonds each atom is attached to. But then when you look at it a little bit farther away, you see the material as a continuum with these little point defects, right? And this gives rise to the fact that the energy will keep this in mind. So it's kind of an elastic energy defined for a wannabe deformation gradient. I say wannabe because failure of being a deformation gradient is present. But then there's also, associated with it, there is also a topological energy, which is defined in terms of where the defects are placed. And there's going to be a finite number of them. So then we want to do energy minimization under a kinematic compatibility or incompatibility constraint. And the idea is to look at this. Dislocations and disclination lines are really, really complex in a material, and they're curved lines, usually loops. But the modeling so far is pretty accurate when you consider them as straight lines, so you zoom in very close to them, and so you can work in the cross-section. So for us, a defect line would be just a vertical line in a cylindrical material, so we can work in a cross-section in R2. And then if U is a displacement, then typical notation is its symmetric gradient is the strain, and then up to the elasticity tensor, we get the stress, which can be written in terms of Delaunay constants in this way. Right, and then the typical elastic energy is the quadratic energy, which is given by sigma double dotted with epsilon, and it assumes this form. And in terms of sigma, it can also be written in this way. So this way is pretty interesting because it's got quadratic terms in sigma. So this is the norm squared, and this is the square of the trace of it. Nu is the Poisson ratio, and epsilon, capital E is the Young's modulus. And usually the assumptions that one makes on Delaunay constants are such that the C turns out to be positive definite. So this is an energy which behaves quadratically, and it's fine for minimization purposes. And what is typical to do in the engineering literature is to introduce this Airy stress function, or also called Airy potential, which is something whose second derivatives take the place of the components of the stress tensor. Not quite in a way that it is its session, but you scramble them around. So the XX component of sigma is the YY derivative of V. The mixed ones are the mixed derivatives with a minus sign coming in, and the y component of sigma is the second derivative of v, right? And if you do so, the equilibrium equation, that would be divergence of sigma equal to 0, is automatically satisfied in this sense because of cancellations. So engineers like this very much because they don't want to work with that, because that's given for free, and then they can focus on other things, on the Airy stress variable. And in this way, if we have this mapping, then we can rewrite the energy curly F in a way that it involves only the second derivatives of V in this fashion here. So the norm of sigma is exactly the norm of the Hessian, and the trace of it is second derivative in y plus second derivative in x is the Laplacian of V. Right? And so we call this curly G. So our idea would be to minimize this elastic energy curly G, but then we need to take into account the presence of these defects. It's a classical result, very old, by Saint-Venant, that says that there is kinematic compatibility if the double curl of epsilon is equal to 0. So now don't mind the capitalization of the letters because it's done in a way to account for the dimensions. Saint-Venant wrote this for 3 by 3 matrices. We work in a 2 by 2 environment, so they need to be completed to a 3 by 3 matrix, but still, think about the double curl. Or call it INC as incompatibility, as some authors do, and that's going to be the same. And then kinematic compatibility boils down to having this incompatibility operator to being equal to 0. If we have curl epsilon equal to the measure of the defect, some way to say that there are some defects, that this is a good measure of incompatibility, okay? And it's also a classical result by Saint-Venant that so having curl of epsilon equal to 0 is equivalent to the fact that epsilon is the symmetric matrix, is the symmetric gradient of a displacement, right? So this holds for, say, regular fields, say at least of class C3, because you can take classical derivatives up to order 3, which is like twice for making the symmetric, for making the symmetric gradient, and 2 more for the curl operator, and that you would be fine. But then using continuous function or even 3 times differentiable functions is not suitable for doing variational analysis. So ideally, this would be will have to be set in a much weaker setting. At least this one should be weakened in a proper way. And there are results in this setting due to Cierlet and also J. Monet and Krasutsky that say that the same idea of the Saint-Venant principle holds true if you set the equation of incompatibility in H-2 and then you look for fields that are of class H1, which is the general setting in which you place yourself to do elasticity, for instance, right? So you would look for a deformation which is of class H1. And in this way, also, you can obtain the fact that if this exists, then the displacement is unique up to rigid motion, because rigid motions are neglected in taking the symmetric gradient, right? So let's see the compatibility, or better incompatibility conditions, a little bit closer. And if we set beta, if we call beta the gradient of u, which is also some other standard notation in the literature, then curl of a gradient is always equal to 0 if the field is differentiable, right? Twice differentiable. But then if the curl of beta is not equal to 0, then you can say that it is equal to some measure of these defects. And so what you can propagate down here starts failing a little bit, because you need to account for this alpha thing, because the symmetric gradient epsilon would be, what would it be? Would be the symmetric part of beta plus the skew part of beta. And then if you take its curl, the curl of beta will go to 0, and then the curl of the skew symmetric part can be written as the negative gradient of a field f, of a function f, actually, right? And then if you take the curl another time, then you got the curl of the gradient, which is equal to 0, so this last equality is all right. But then if you start taking alpha here, then the alpha propagates down there, and then if you take the curl of this, you've obtained the curl of alpha there. And the other thing that can fail is that nabla f is not really a gradient itself. Then I write it in quotation marks because that's the way you find it in the physical literature, but it's, of course, it can be formalized. So then it's equal to some H-1 field. kappa, whose curl we can call theta, right? And I highlight these two things written in this way because now if you consider, as we do actually here, alpha and theta only Dirac masses, so basically a finite combination of deltas placed somewhere conveniently, then this is the incompatibility condition that is suitable to place on your minimization problem to keep track of the defects. So alpha is the presence of H dislocations, each of which has Berger's vectors Bj, and I count a capital J of them, for instance, and the theta is the presence of wedge disclinations, the thing we did with the Zakatote. And the measure of the disclination is usually called the Frank angle, which counts how many fractions of pi over 6 in the hexagonal lattice you're mismatching when you open or close your material. And it's important that they're written in this way because already, so we see that we've got delta functions here. The bold delta is the Dirac delta, placed at xj or yk. But then here we take the derivative of delta. The derivative in a direction which is dictated by the Berger's vector, which I'm going to explain a little bit in detail later, and then you will see that this one here is the natural generalization of what I do along E1, for instance. And so this tells us that there's a derivation relationship between the presence of disclinations and the presence of dislocation, which also should be tracked in the energy and in how we see it in the scales of interaction between one and the other one. Okay, so now what you usually do when you try to do variational calculus, you minimize the energy, and so to minimize the energy, you look for solutions of the Euler-Lagrange equation associated with it. And in the, let me say, the physical world, the Euler-Lagrange equation reads like this, right? So we have the divergence of sigma, which is equal to 0. Sigma was C epsilon. Sigma dotted with n, or sigma applied to the normal is equal to 0 of the boundary of your material. This is stress-free configuration. And then we have the incompatibility, which is curl of epsilon equals to minus delta. I wrote everything here in the epsilon variable, minus theta, sorry, in the epsilon variable just to be a little bit more consistent. Then in the Airy world, we have conversions, right? So the curl operator becomes the B-Laplacian, which is a very nice, say, fourth order operator. And then there's a price to pay, which is numerical coefficient, which we can disregard for the moment. So basically, if there were no defects, we would be looking for biharmonic Airy potentials. If there are defects, we look for Airy potentials which are not biharmonic anymore. And then the boundary condition sigma n equal to 0 gets translated into the Hessian of V applied to the tangent vector at the boundary to be equal to 0. So it's in this setting that we want to study what happens a little bit. And we can prove a proposition that says that these two problems are indeed equivalent. So you can study your defective elasticity problem in the physical world, as well as you can study it in the Airy variable, right? And as it happens for dislocations, where you can find, say, the source of a dislocation, so the deformation that's due to the presence of a dislocation somewhere in your material with an explicit function, you can find it in many papers. You can go back to a book by Mushkelishvili that's about 700 pages long, and you look into that as well. In the same way, we can find a function who is not biharmonic, but its bi-Laplacian operator gives back the delta centered at a point, and it has precisely this form here. So it's rho squared log rho, basically. Okay, so the 2 here as a power you can bring outside, but there's a square here in the distance, and there's a logarithmic contribution there that are very important for the scaling that we're going to see later. And of course, there are some other pieces that you can add to this one, but they are biharmonic, so you can add them at your convenience or disregard them. This is the core of the presence of a disclination. So taking the biharmonic, the bi-Laplacian of this generates the delta centered at the origin. And then we can also prove an interesting geometric lemma that says that the boundary condition here, so Hessian applied to the tangent equal to 0 holds, if and only if the function v is the trace of an affine function at the boundary and its normal derivative is the normal derivative of that precise affine function. And this is useful because if you think about if you think about it, these affine functions are in the kernel of this boundary condition here. If you take the Hessian of an affine function, you see 0. So then you can move or wiggle your solution a little bit by an affine function, and it will just stay the same, all right? Let alone taking four derivatives for computing the biharmonic operator. Which means that you can, if you have, say, many disclinations, you can pick your favorite one when you do some sort of corredius approach, as we will see later. You can say that affine function is equal to 0, and then all the other ones will be just difference of affine functions. So after doing that, and this was preparatory, was a preparation for seeing how things work in the Airy variable. So after doing so, we would like to find a suitable energy to place on a material that accounts for the presence of disclinations. And the one that we suggest is this one. So we get the elastic energy as we had before, the curly G, which was the F of sigma, just translated into the Airy world. And then we take formally, there would be the duality, take the product, if you want, of the measure of disclinations theta with the function v that's the Airy variable, right? So this doesn't have a sign, keep it in mind. This one is quadratic, this one doesn't have a sign. And as we will see in a couple of clicks of the pointer, then the energy, the minimizer would be indeed negative. And by what we said before, minimizing this I theta over the functions that obey the boundary condition is the same thing as minimizing the energy over the functions that obey our favorite boundary condition, which is flipping the affine function to 0. So we work in H to 0, which is a much nicer space than this one. And we see actually what is the solution to the minimization problem. So we take a Frank angle, which is non-vanishing, and it would be discrete, of course, but then take any S and it works fine. We take a point in R2 where we center our defect and the radius R. And then we say that the solution, so this function here, which is obtained by suitably rescaling and resizing the function V bar that I introduced before, is a solution, is a minimizer of the energy, right? So its elastic energy can be computed explicitly, and it gives this contribution here. The duality part here can be computed explicitly as well, and it's minus twice the other one, right? So when you put them together, the energy is going to be negative, and the contribution of each disclination comes in with the square of the Frank angle. So that means that you really don't see in the computations of the energy if the disclination is positive or negative. It just needs to be there for giving this behavior. And we also see another interesting fact, which is the fact that the minimum of the energy scales with the square of the radius of the disk. So scales with the square of the size of our domain, which is drastically bad, because if you take a large domain, then the energy is going to be very big in absolute value, right? For dislocations, it is different. So those that are used to thinking in terms of dislocation, the energy of a dislocation in a ball of radius r scales with 1 over the log of the radius r. Actually, you just need to concentrate to look at the place very close to the dislocations to see that behavior. So now, how do I want to make these two objects, these two sorts of defects, communicate with one another? The way I want to do it is by repeating Eshelby's construction, and I place a dipole of disclinations, positive and negative 1, at a distance h across one another. And for convenience, let's put them on the x-axis. And then I want to study the limit as h goes to 0. And the idea is to do this construction here. Take your favorite Zaka-Tote, you cut a wedge of the Tote, and then you slide the wedge on the x-axis, and you place the two tips in these two ways, in a way as I did there. And then you glue it together again, right? So in gluing it together, you will obtain, as per Eshelby's construction, an edge dislocation, whose Burgers vector is directed perpendicularly to the director from the minus to the plus sign, as I depicted here, in the limit, of course, right? Because here, at this point, the mismatch is perpendicular to the radius, but then when you close it and send h to 0, then it will become vertical. So to do this, the dipole is associated with this measure here. So delta is placed at the plus minus locations. And since the problem is linear, then we can do superposition principle, and we take the V bar given by this translates of the original one, and this is a solution to the Bahamonic equation with datum the theta h, right? As I write here. So now the important thing is, how does the energy of this VH bar rescale in terms of h? So we look at what happens in an annulus, for instance, of radius small radius r and big radius capital R, and we can prove that there exists a constant such that in the annulus the energy scales like h squared, right? So this one, the right-hand side does not depend on h anymore, but then the energy basically scales like h squared. And moreover, if we compute the elastic, sorry, not the energy, the norm of the solution, but the energy, the elastic energy scales like h squared log h, which gets together some information about the size of the domain in a way, or like the distance between the two defects, and this log h behavior, which is typical of h dislocations. And indeed, we can see that the minimizer of this of our dislocation energy I theta, if we consider it, then we have these two behaviors here. So both the elastic part and the full energy scale like h squared over h, and they get to the same limit with opposite signs as we expected, because the contribution of that duality was negative. All right. So the Euler-Lagrange equation that is satisfied by that VH is this one. So we get that by Laplacian up to the constants in front is equal to minus theta h. And then if you formally take theta h over h and you send h to 0, then you basically recover the x1 derivative, right? So the partial derivative with respect to the x1 direction. And so the idea would be to see what happens formally to the rescaling of VH divided by h itself, so that you can divide by h the whole equation and see where it goes to. All right? And so we can prove that indeed this is the V is the Airy function associated with the elastic stress field of one edge dislocation. Now we got to the other type of defects, whose Burgers vector is S and it's vertical along the direction E2. And what comes next is the energetic equivalence of these defects, because Eshelby said, okay, do this thing with the wedges, remove them and reglue them together, and then naturally you would come out with this field, but then there was no energetic equivalence involved in this paper. So the way we do it is this one. So we basically approximate the duality of the measure theta of the defect against the function by this sort of discretization procedure, okay? And then if we rescale the function by h, then we get the following thing. So the elastic energy scales by h squared, because it's quadratic in the w variable, or v as I wrote before variable. And if you do h over here, then you obtain this incremental quotient, right? So this incremental quotient is the one that will converge to the derivative in the limit. And so it makes sense to study the energy divided by h squared to see what comes out, right? So the first thing that we do is to divide the energy by h squared and study this limit, and we obtain the limiting energy on the ball without the puncturing, and then we obtain this term here, so on the whole domain, and then we obtain this term here, which is some contribution coming from the boundary of a ball of radius epsilon. Now epsilon is larger than h, sorry, so it's much larger than the distance of the dipole, but say smaller than the size of the domain, so you put a scale in between. And I call it epsilon because it's the same epsilon that is the one of the co-radius approach, all right? That is customary to do for dislocations. So we can prove a bunch of results. So there's a unique minimizer of this energy in the suitable function space, which was listed here, this one, the one that keeps trace of a fine boundary condition at the boundary. And it converges in H2 strongly to a minimizer of the energy where the parameter H has shrunken to 0. So it converges strongly in H2 to the energy of what you get when you fuse the two disclinations and you see one dislocation. And then the behavior of the energy scales like log epsilon, or log of minus like 1 over epsilon, which is the one that we expect. And we know that we cannot take this limit here because this limit here explodes. So what we wanted to do was to try and recover the asymptotic expansion of the energy, better of the renormalized energy of Cermelli and Leoni in a celebrated paper dating back to 2005. And actually, we managed to do this at all scales. To do this, we have to work on the other way. So the first thing that we do is that we assume to have a distribution of dislocations now, and we approximate them by dipoles of disclinations in the following way. And these projections and rotations are needed to keep in mind that the sketch that I depicted before needs to be rotated for any Burgers vector that we have. Okay. And then we obtain something that converges to the minimizer of an energy, which now depends on the measure of dislocations that we've got in this domain omega epsilon alpha, which is the perforated domain where we cut out the cores of radius epsilon at the centers of where the deltas are located. So this is what I wrote before, and the usual trick to do this is to decompose your field W into two contributions, what I might call the elastic and plastic part. So the plastic part is the one given by the defects, which we know because I told you at the beginning that there was the solution for one disclination, and it's collected in this capital W alpha. And then anything that's left, ideally what the material does to rearrange itself and cope with the boundary conditions dictated by the presence of the defects, goes into this small w tilde, which would be the elastic part of the deformation. And we study, so minimizing the energy in terms of the full W gets two contributions which we can measure and gets another contribution which only depends on the elastic part. So minimizing this one is the same thing as minimizing this one where all tildes are present. And this is just the development of the double products when you do this one tested against itself. So what we can prove is the following result. We get convergence to a minimizer strongly in H2 local of the puncture domain because we cannot get to H2 of the full domain, as I mentioned before, because the energy will explode to infinity. And we get that the W satisfies a bilaplacian equation in a way where the source term is given by the dislocations that are present in the body. This is the green part. I think that it was, sorry, not green, it was like the blue part that I gave before at the beginning when I wrote the alpha measure. So this would be the alpha measure. And then to do this, we apply that decomposition and use these two following technical results that are basically an epsilon independent Poincaré type inequality, which was obtained in the paper by Cermelli and Leoni, and then we could reobtain again in our setting, this one here. And the following proposition here that tells us how the energy scales. So what is the value of the energy in terms of the limit for the elastic parts. Okay, and then we obtain that this function here in the limit is indeed biharmonic. So that was the elastic contribution which doesn't see the presence of the defects, and its energy converges to the energy in the limit. So the final slide is about the renormalized energy, and actually we can obtain that the energy scales like a part that diverges like log epsilon, which is what was expected. Two contributions, F and little omega epsilon. One does not depend on epsilon, the other one is infinitesimal with epsilon, so we disregard them. The most important part is the F, which is called the renormalized energy. And this renormalized energy is a topological energy that takes into account where the defects are located. So that's why it's indexed by the measure alpha. And it can be seen to be split into three different parts. The so-called self energy, which is the energy happening because these locations are there. The interaction energy, which is the energy contribution given by the interaction of these locations with different Burgers vectors. And the elastic part of the energy, which was the energy of the tilde part that I wrote before. And so the explicit expressions are here, are quite complicated, but for those of you who are experts in the field, should be pretty familiar. And I just wanted to point out that we really do get the Cermelli-Leoni expansion at all scales with matching terms at order log epsilon at the order of the renormalized energy. This little f has got a horrible expression, but it's of order 1, and the little omega epsilon is order of epsilon. Yes, so this is what I wanted to tell you, and I thank you very much for your attention.